Okay, in the first stats course, we're used to solving such problems as we're told that x, a random variable x, follows some kind of distribution, let's say a Poisson, with some parameter lambda, say 2.1, and then you ask to calculate probability that x is bigger than or equal to 3. Or we have a question that says, have a random variable y, it's binomial, n is 10, probability of success is 0.6, find the probability that y is equal to 3, and so on. Okay, now in each of these cases we have a model, a probability model. A model consists of the data and also a parameter. Okay, so in the Poisson the parameter is lambda, here it's 2.1. In binomial the parameter is n, which is 10 in this example, and probability of success 0.6. In all those kinds of applied questions you're told what these parameters are. So parameters are given, and then you just ask to calculate probabilities of events happening. But in real life, in modeling, parameters are unknown and so have to be estimated, and the MLE is one such a method for estimating the parameters. So before we can calculate these probabilities, we actually have to find what these parameters are. This one. For a binomial, this one is usually known. And that's the subject of this video. I'm going to give you an intro on how to write down the likelihood function, then we'll look at a couple of examples, and then we'll finish off by mentioning when the standard method of finding the MLE fails. Okay, so we have a sequence of random variables, and they come from a distribution, from the same distribution. Let's denote it by f. And let it depend on only one parameter. Let's call it that parameter theta. Okay, so in step 1 of finding the MLE, we have to write down the likelihood function. Okay, the idea is this. Given the data, okay, this is my data, what's the most likely value of theta that is consistent with seeing my particular set of data? Okay, these will actually be like numbers, and then you're gonna, and this is like the model, a certain distribution, and this guy is unknown. So the question is, what is the parameter that is consistent with seeing some numbers? For example, if we have okay, if we flip a coin 5 times, let x be the number of times it falls on the head. Well, if we do it first time, that we might get 3 out of 5 heads. Second time we might get 1 out of 5 heads, and so on. That's an example of realizations of the data. Okay, now to write down the likelihood. The likelihood is a function, and the argument here is a function of the parameter, and we define it like this. It is the joint PDF of all n observations. Now, what does this guy mean? Think back to basic stats. Remember, you know what this guy means. Event probability of A and B. That's probability of A and B simultaneously happening. This is what this is basically, with the commas there instead of the intersection, and we've got n observations as opposed to, let's say, 2. Alright, that's kind of the way to think about it. And before I continue as well, let's also look at this. Recall that this guy here, this probability is called the joint probability. If we're interested in only probability A or only probability B happening when there are two events, say what's the probability of A happening when A and B could happen, this guy is called the marginal probability. Okay, A. Okay. So we can break this joint probability into the following. If we assume this, if we assume that the x's are independent, so if the random sample, the x's are independent, so this outcome here will not depend on this outcome and so on. Well, then we can say that this joint probability can be broken down into the product of the marginals. What result have I used? I have used this result that you all know, probability of A and B, it's two events. If A and B are independent, you know it's probability of A times probability of B. Okay, so that's what I've done here. This is this. This is just the product of the individual events. So that's the joint. These is the product of the marginals. Why? Because the x's are independent. Okay, so if I put by independence there. Now the shorthand to see this, write this, you might have seen some textbooks, is to write this great big pi sign going from 1 to n of f x I theta. Okay, and that's just another way to write this. This is longhand, this is like shorthand. So you've seen the summation sign. This is like, and you know what that does, that just sums of all the individual elements. This is like the opposite, this is like the product sign, and it does that. Okay, so that's the likelihood. Okay, now we typically work with, because it's easier to work with, the log version of this. So we take the log of this likelihood, let's denote it by curly L, natural log of L theta. Okay, so what do we do? Well, let's take it from this line here. I want to take the log of f Now we use this rule. Let's have a review. We know that log of a product is equal to the sum of the logs. So this becomes log of f. Okay, excellent, let's write it. Plus log of fx2 plus dot 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 plus final term log of f xn theta. And the shorthand way to write this is sum I equal 1 to n f log of f xi theta I. So you can see that by taking a log, it's like this product has gone into the sum sign. Alright, it's this guy we want to work with. I want to, as the name suggests, maximize the likelihood function. So we've got the likelihood function, the log likelihood. Now we've got to maximize it. Maximize it with what? With respect to the parameter. Okay, a quick recap of maximize single variable calculus here. If we have such a function, if we have something that looks like this, okay, this is say theta, f theta. You know how to, where the that's like the wrong plot. Sorry, that's not a great plot. That I'm going to maximize something. That's change that. Let's do this. Okay, so we've got a function here which depends on the values of theta. Now you know how to go about maximizing something like this. Oh, in fact, even let's just call it x instead of theta, because you're used to talking about x's from school. Okay, so here we've got to function. Let's not even talk about y. Let's talk about y. So y equals some function of x. You know how to find the stationary point of something like this, the maximum here, because it's at the stationary point, isn't it? So that's where dy, the gradient there, is 0. And you have to find the x value along here where you got that happening. So that's what we're doing with the likelihood function as well, log likelihood. Now let's have a look at a couple of examples. First example, let my x's be independent random variables, and they are from a Poisson. No, let's say an exponential distribution with parameter lambda. So we have the PDF here, fx I is equal to lambda x for x bigger than 0, 0 otherwise. Okay, now why put I here? Because we've got n, small n of these random variables, so we put an I here. Alright, could also put an I there as well. So let's write down the likelihood. Let's do this real slow. So the parameter here is lambda. So before I wrote theta, right? Because that was just generic, but here it's actually lambda. So we write lambda like that. And that's equal to the product of the marginals. So this is like the marginal PDFs. So this is like, this is the marginal PDF. So this is for first observation. So I put 1 there. Let's put brackets around it to see that's the first one. And the second one. And you can see a pattern repeats. So you get the final observation xn. Okay, now it's just tidying stuff up here. Now can you see, let's group all these together. How many lambdas do we have? Okay, common wrong answer is n times lambda. That's not the case. Let's just group the lambdas together. Then we've got lambda times lambda times lambda. Okay, let's group all these e's together. E to the minus lambda x1, e to the minus. By the way, I'm doing this in great detail. You won't actually need to write this, every single line of this. Alright, so if we look at this, this you can see is not n times lambda. It is lambda to the power of n. How about this? Okay, for that, note this rule. E to the a, e to the b is equal to e to the a plus b. So this here will be equal to e minus lambda. Now lambda here is a common factor, alright? So I could take it out, or if you wish, let's not take it out, let's just do everything little by little. So that's so applying this, the property of exponential, is simply this. Let's tidy that up. We've got lambda to the power of n. This, can you see now, is a common factor of lambda. That's what I was saying before. So take that out. That's a minus lambda. Remember minus and a... Right, so here, now you've got x1. Now, remember a minus and a plus makes a minus. You've got a minus here, so it's plus x2 plus all the way to xn. Alright, when you take that minus lambda through the bracket, you're going to get this. To make that look neater, we just can write e to the minus lambda sum of xi, where I goes from 1 to n. Alternatively, you could write n x bar. That's the same thing. Okay, so that is the likelihood. But we want to work with the log likelihood. So let's take the log of that. Curly L, lambda is the parameter, equals log of L. Okay, now, so log rules. I'll do that again. So you know that log of A times B is equal to log of A plus log of B. So take that is one thing, that's another thing, isn't it? Let's put brackets around that. Just clear clearly. So that's one, that's like my A, that's like my B. So I'm going to have log of lambda n, okay, plus log of E minus lambda, sum of xi. Okay, now some more rules of logarithm rules. Log of something, say y to the a, you take that down, don't you? So that's a log y. Also, you know that a log is like the inverse of an exponential, so that'll just go, so you're only left with that. So this can be written as n log lambda, and it's going to be a minus, because that's gone, that's minus lambda sum of xi. Right. Okay, well, that's the first step, and that is the log likelihood. Before proceeding to solving this, I find a stationary point, because we expect this to have be able to draw a picture here, lambda along here, log likelihood to be like here, and we'll have some picture, a plot of this guy here, and we want to find the stationary point and show it's a maximum. So wouldn't it be interesting just to see what this guy might look like? So let's do an example on Excel. Something that you can do, see, so I've picked Excel. Excel doesn't do great charts, but I'm going to use it. Let's pick sum of xi to be 37. You can do anything you like here. Let's say n, let's set that to 15, okay? Let's pretend that's our data. So we've got n here, we've got sum of xi is 37, so the only thing we're changing is lambda. So we're changing on lambda, and then we're plotting the values of lambda, of log like that comes out. And likelihood. Why don't we do both? Okay, so this is my setup, something you can do. So I've set n to 15, sum of x to 37, okay. So what I've got here is my lambda, log likelihood values, so just enter the formula. And also I've got the lambda and likelihood. Now maximizing the likelihood, this is one thing about MLE, maximizing the likelihood is the same as, you get the same result as maximizing the log likelihood. So let's bring over the picture for the likelihood here. So here's my values of lambda running along here. Remember, we're trying to find the lambda that maximizes the likelihood function. And you can see it kind of curves like that. So the peak is somewhere around here. It's just short of 0.5 for this problem. Do we get the same with the log likelihood? Well, here is the picture for the log likelihood for this problem. So you can see that this is again the lambda values, and this times the log likelihood. You can see the scale is different. This is like all positive, these are negatives, but our maximum is occurring here, just short of 0.5, so it is consistent. In fact, there should be. Okay, so we're working with this thing here. Now, from single value variable calculus, we know that we can solve this by finding the stationary point there. So it's going to look like that. Okay, that's what we've just found out. So how to do it? Okay. This is finding the stationary point, otherwise known as solving the first order condition. So we differentiate the log likelihood with respect to the parameter. Okay, this is like your usual in your first year calculus dy by dx thing. And now we use some rules, log rules. So n Now the derivative of if y is equal to log x, dy by dx is equal to 1 over x, the absolute value. Okay, but here in this problem x is bigger than 0 because you're told it's an exponential. So we have here 1 over lambda. Okay, and lambda can't be negative, it's a rate parameter anyway, yeah. Okay, and then minus, okay, sum of xi is just a constant, so that looking at this is like looking at that's like a constant, so it's just looking at lambda times a constant, say a. Alright, y equals like that, so dy by d lambda would just be equal to a. So here this is going to be sum of xi. Okay, now we want to solve this so it's equal to 0, but when it's equal to 0 it's not any value of lambda that makes it equal to 0, it's the solution. So let's just put this in red to show you that's the only thing that's changing. N is fixed, sum of xi is given for this particular sample data. So we just have to find this lambda, appropriate lambda that makes this equal to 0. So we do n over lambda minus sum of xi equal to 0. Now when equal to 0, let's do it in red. When it's equal to 0, it's not any particular value of lambda, it's the solution. So let's call that hat. Then we rearrange this, so therefore take this sum to the other side, take n down. You can see that this is sum of xi over n. In other words, sample mean. Or rather, that's an error there. If I take that across, I'm trying to do two steps at once, right? This is take that across, take that down, and 1 over left and right hand side, and that gives us n over sum of xi, which is equal to 1 over x bar. So the MLE right here, that is equal to 1 over x bar, or that. So for my problem, it would have been, so you can see here, x bar will be x bar is equal to 37 over 15. Therefore my solution will be 15 over 37. Okay, so equal 15 divided by 37, 0.4, that's the solution. So you can see roughly that this is solution. It's 0.4, about 0.4. Okay, and that's it. That's the first example. There is one thing to mention, although you could usually stop here if it's your first course in stats, and that is, if you've done single value variable calculus, the thing is, how do you know that what you found is not a minimum instead of a maximum? And if it's a maximum, how do you know it is not a local as opposed to global maximum? So what we need to do really is look at the second derivative. If it's a maximum, that thing should be negative. If for a max. Okay, so if we do it for this one, dl second derivative respect to lambda. So let me just rewrite this bit here as lambda, this bit here lambda minus 1 minus sum of xi. That's what this is. So if you look at the derivative of this guy again, take the minus 1 down, minus n lambda minus 2, and this is minus 0, constant respect to lambda. N is positive, lambda is positive, so indeed you have something which is negative. So it is indeed a max. How do you know it's not like a global max, or you know, so how do you know, if we didn't look at this picture, how do we know it didn't do something like this? So what we've got here is that, let's say, lambda can take values from here all the way along here. What you can see is then you've got 2 boundary points and you've got 2 turning points. That's the max. So we'd find that, and we'd find this, and we'd see that's a minimum, that's a max. But how do you know that this is not the MLE? Because here it would not be the MLE, because you can see here that the value, the lambda that maximizes the likelihood, is this one. This would be the MLE. In other words, we ought to be checking the, we should be careful, we should be watchful of the boundary values as well as the interior values. The method that we've shown you is finding it for the interior solution. How do you know it's not on the boundary as well? So ideally you check the boundary as well. On the other hand, if there's a shortcut, and that is if you know there's one turning point and it is the max, then it must be the global max. Because it can't be a turning point, because if it was, sorry, it can't be at the boundary, because if it is at the boundary you'd have to turn again, in which case you'd have to find more than one boundary condition. I mean, you'd have to find more than one stationary point. Okay, I'll do one more example, and this time let's say that they're independent from Poisson. So this time we've got something that is discrete. Okay, well, for Poisson, P xi, that's typical notation used, isn't it? Lambda xi eta minus lambda for xi factorial for xi equal to 0, 1, 2, and so on. I put I again because it's for each of these guys, and we've got n of them. Now I'm using the P notation instead of the F notation. You can use F if you like, but usually when we have a discrete random variable, we use P. Okay, we call this the probability mass function. Okay, so likelihood lambda is the parameter, equal product of the marginals. Okay, can I just write this down? So doing the same steps as before, you have lambda sum of xi e minus n lambda. This is very similar, you see, to the exponential with that guy there. And down here, what we're going to have x1 factorial, x2 factorial, all the way to xn factorial. I take the log of this guy. That's, use the log rules. So I'm going to have sum of xi, sum of this guy, block by itself, times lambda. Okay, let's stick it there. Minus n lambda minus log of all this. Now because we can save ourselves some time here, because you can see that this is it's constant respect to lambda. It doesn't involve any parameter. So when you're going to differentiate this thing to find the stationary point, it's going to disappear, isn't it? Yeah. So some people just write constant instead of bothering to write this stuff down. Or if you've got some more messy kind of model, you can just write constant there, or say that proportional to this guy and drop this is another way to write it. Okay, so there, that's my log likelihood. Differentiate this thing with respect to my parameter, lambda, sum of xi minus a minute, I missed a log there, sorry, log that, yeah, yep. So I've got over lambda minus n minus 0. And the value of lambda that sets this to 0 is therefore sum of xi lambda hat minus n is equal to 0, or this is equal to n. Therefore take that down, so lambda hat is equal to sum of xi over n x bar. To check that it's a maximum, look at the second derivative of this guy. And you're going to see that it is negative. So that's minus lambda minus. Okay, that's positive. Lambda is positive. That's a minus, so it's negative. Therefore, indeed, is a max. And since it's only one max, it's only one turning point and it's a max, it's the global max, so it is the MLE. Okay, so for most of us, all we need to do is be able to solve for the MLE, so write down the likelihood function, differentiate the log likelihood function, set to 0, and just solve it. No need to look at the second order conditions. So that's all we need, and for a great deal of models this will work. But does this method always work, based on solving the turning point? The answer is no. Let's say we have a likelihood function that looks something like this. This is the range of values that lambda can take for this model. Then can you see that the slope is increasing with theta? You're not going to be able to, when you try to find the first order condition, you're not going to be able to find it, because there isn't one. You can't. There is no dl or d log of l theta equal to 0 in this range of theta. What you can see though by visual inspection is that MLE is here. It's the boundary solution. This theta is the value that maximizes the likelihood. Okay, so sometimes these, if you can sketch a picture like this, it can help you a great deal, but this is for simple problems. Okay, I think that's enough for an introduction to MLE. Okay, thanks for watching.